Good morning, guten Morgen. My name is Erik Eberhardt. I'm a professor in rock engineering and geotechnical engineering at UBC, University of British Columbia. My background has been mostly in rock mechanics and rock engineering, and as you'll see throughout the course of the week, and just from some of the topics that Simon and Aldridge already covered, it's been very much, my direction has been process and mechanism directed, using different tools. And that's one thing I'll emphasize through my lectures here, is thinking about what these different things, numerical modeling, instrumentation, mapping, as all tools that we use to approach a problem. And the problems I look at are range from tunneling problems to underground mining problems to those on surface, rock slopes, and rock slopes in mining. And in between my academic work, when I was doing consulting and working for a few mining companies in open pit mines, I was doing pit wall stability, so looking at slope stability from a mining context. And it's difficult and it's complex, and I thought that it was a problem that really requires a lot of thought in the decision making that you do on a day-to-day basis in terms of doing a stability of a pit wall. But after doing that for some time, I came to Switzerland, and I worked here for 6 years as an Ober assistant actually in Simon Löw's group. And I started working on natural slopes because there's sort of a shortage of mining slopes here in Switzerland. And when I started working with natural slopes, I really fully started to understand the complexity that's involved. Now, from a mining context, the complexity is usually in terms of trying to understand the geology, the kinematics, the behavior and the stability of a slope. But at least in terms of time constraints, you have a good understanding of the failure process. Because you go to a slope that's in a natural equilibrium, and then you start modifying it. We started cutting into the slope, we're starting to mine it, we're reshaping the geometry, and so that we sort of know the t equals 0 of when the instability process begins, basically when we started the mining. And when I came to Switzerland and I saw things like the Randa rock slide, I'd sort of scratch my head and say, well, why did Randa fail when it did? What was so unique about 1991 that it failed? And some people would say, well, heavy rainfall or snow melt. But then you'd look at the precipitation records, and it would be no different than the rainfalls that it would have experienced in the years before. And so when we get to natural slopes, we get into a very complex system where, as Simon said, when you try to use some empirical techniques to predict failure, sometimes you're right, sometimes you're wrong. And it's just the amount of uncertainty that's involved that we'll probably try to emphasize quite a bit during the process of this course. So we start off by saying that in the context of rock slopes, a rock mass is a very complex system. We have a number of processes working there towards creating an unstable situation. Might be related to the geology. Is there structures that are controlling that instability? Is it tied into the mechanical behavior where we have weak rock? Maybe a combination of strong rock on weak rock causing some type of spreading mechanism. Groundwater or infiltrated water through precipitation is usually a key player, so there's a hydrological framework that we have to understand. The geomorphology, and this is where we get to natural slopes relative to mining slopes, that geomorphology plays an interesting role because in a natural slope, in most alpine environments, there's been a history of glacial activity that has come through, it's undercut the slope, it's changed the slope from maybe a stable configuration to one that's been oversteepened. Maybe there's unloading or rebound joints that have weakened the rock mass. So almost the t equals 0 in terms of when that slope started to become unstable was basically during the retreat of the last major glaciation. And then from that time, over the last several thousand years, that slope has just been gradually weakening and weakening, moving towards a failed state. In some cases, biology might play a role in terms of tree growth, so especially in soil slopes, the strength that's provided by trees is an important component to a natural system. We deforest it, and then we might be causing an instable stabilization. And because of that, the human or the anthropogenic side of things, a lot of times we're also responsible for what basically leads to interactions with the triggering event. So when we talk about causes, we're not talking about heavy rainfall or the heavy snowfall that delivers the final impetus for failure. We're just talking about an overall a combination of factors that create an unstable situation. A trigger comes along, an earthquake, a heavy rainfall, and we lead then to our failed state. And time is the question mark here. Again, as I said, from a mining perspective, we have a better grip on time. With natural slopes, time really throws sort of throws a problem, an extra dimension to the problem in terms of trying to understand and predict behavior. So often, we're dealing with a very complex system here, and because of that, the geology, our understanding of the geological structure, the rock mass property, the rock mass behavior, the groundwater, the data that we have is very limited. We're literally scratching at the surface of a problem that's much deeper. And because of this, the way that we apply our analyses, the way we use numerical models, the way we use analytical solutions, the way we use empirical techniques are very limited. Because the data that we have is likewise, that are feeding those systems are limited, and we can never know a system completely. However, we can start looking at the different tools that are available to us and try to gain as much knowledge as possible. And then again, as we'll see throughout the week, when we do analyses, we're not working towards a single answer. We're looking towards a range of answers, a range of possible behaviors that interact with our judgment and our experience. And so we're not using these as just an answer that comes out and just believe whatever the computer tells us. We're using it not for a substitute for thinking, but we use it as an aid to our thought process. Well, we have our complex system here, our slide processes, and we generally start with a geological investigation. This is the key data set, and as Professor Löw mentioned at the very beginning of his lecture, that because the geological model is what we base all our future analyses on, if you get the geological model wrong, most of the assumptions that go into the analyses then it's a moot point. It's meaningless because you're analyzing the wrong problem. So we start off with a detailed geological investigation, mapping not only the different geology and lithological units, but the structures that are cutting them. We'll talk a bit about structure and use of stereo nets as a first indicator of understanding a problem. We'll do that this afternoon and tomorrow. In some cases, we've started to move is into also using geophysics. Because when we're doing geological mapping, we're looking at the surface of a problem of instability that is at depth. We're trying to project from the surface some understanding of geology into the subsurface and what is probably happening in terms of the development of a shear plane and the instability mechanism. And geophysics gives us a mean of helping to develop our geological model by giving us some feeling and some picture for what's inside the slope. But these are really techniques that are being developed almost on a research level. For some more simple applications, geophysics plays a very important role. But for rock slopes, we're just starting to understand how we can use these in developing our geological model. And it's our geological model, simplified usually into a 2D cross-section, that we start basing our analyses on. So this is what we're trying to work towards, is some type of detailed cross-section that gives us some understanding of the geology, what might be controlling failure, where potential failures were developed. This is just a cross-section of the Rando rock slide that occurred in 1991. It's what we use to base our analyses on. If we can go into 3 dimensions, then we even have more complexity. Now, on top of our geological investigation, we then add some type of monitoring if our budgets allow it. So geotechnical monitoring can be very simple. It can be simply just measuring the opening of a crack on surface, a tension crack, and just coming back each year or every several months to measure it, to try to gain some feeling for how unstable the slope is. With a little bit of extra money, we might be able to sink boreholes, and we'll use the boreholes to gain more information about the geology at depth. But we also use the boreholes to measure deformations at depth, so using inclinometers. And the inclinometers might identify certain shear planes that are accommodating a lot of the motion. we would like to combine these, or we often combine these with geodetic measurements. And so even if we can't do borehole measurements because the site location is difficult to get a drill rig to, or the costs are too high, we can usually at least set up a few survey monuments and then geodetically monitor these points to get some idea of block movement and the rate of instability. So we take our geological model and we then start trying to understand some of the physics and the kinematics through geotechnical measurements. This feeds into our understanding of the kinematics of the rock slide. And then with that, we start looking at our different stability analysis techniques. And as we'll see, we have different solutions for different modes of failure. So we have to understand the mode of failure in the geology before we know which analyses to perform, or which combination of analyses to perform, because we're talking about complex systems where usually we need to look at a range of different behaviors to get a full understanding of the problem. And this is basically leading into also understanding of the controlling mechanisms of the problem. What is the geology? What are the rock mass properties? Is it a failure that's being driven by water? And so we have to understand the hydrogeology. Is it a failure that's being driven by strength degradation of the rock mass, intact rock bridges failing, allowing non-persistent discontinuities to evolve into a shear plane? Once we understand some of the controlling mechanisms, this all then feeds in again into a better understanding of the rock slide process. So all of these are pieces of information that we use and that we're collecting. And the analyses, which is really what the focus of this course is also only a small part of the whole hazard management scheme in the decision-making process. So we collect data, and the data collection goes in and it feeds into different aspects of our analysis. We're looking at assessing the hazard itself. We might do this either in terms of deterministic techniques or probabilistic techniques, and probabilistic analyses is something that we've worked into the problems that we deal with because we have an uncertain system. We have a lot of uncertainty in our system. We use models and we use techniques that have been sort of, let's say, promoted by mechanical engineers and civil engineers. And when we're working with engineered materials, steel, concrete, we know how these systems are going to behave. We make the material. We have a nice little table that within a very small tolerance will tell us how that material will behave, how it deforms, what its strength is. But when we get into soils and rocks, these are materials that we have to deal with as is. They're in place. Mother Nature has made them. We weren't around when they were created. And because we're just really looking at them on the surface, we have a very poor understanding of what happens in depth. So we worked into these techniques such as numerical modeling or limit equilibrium techniques. We've worked into them idea of dealing with the uncertainty and probability, and instead of trying to come to a unique solution, trying to develop a range of possibilities. Now, the hazard assessment is only part of the program when we're looking at the overall risk. The other side of the equation is vulnerability. Is there anything, if a slope fails, is it threatening anything, or is it as we have many experiences in Canada, in the middle of nowhere with no one around, and therefore, other than maybe some environmental considerations with fish streams and so forth, it might not be a high impact in terms of the amount of money that you want to spend on understanding or fixing the problem. But of course, in a populated area or a busy corridor for traffic, whether it's a rail line or some type of pipeline, then all of a sudden there's something of value there that's under threat, and so we move towards putting more money into understanding the hazard together with the vulnerability to understand the overall risk. So when we move into data collection, again, we're looking at the geology, the topography of the slope in question, and some of the characteristics of the rock mass, the strength, the groundwater affecting it, maybe some considerations regarding triggers. If we're in a mining environment, we have blasting that might produce dynamic loading, or we might be in a seismically active area where earthquakes then become a consideration. The geology, well, the mapping, again, we're mapping not only geology, but some understanding of the geotechnical properties, looking at structures that are crossing, so we might be mapping different lithological units. But what we really want to separate are things that are important towards controlling the failure and things that might be too fine a resolution that won't work into our analyses. We might have small little outcrops of rock units that are different than the major rock units. But if we're not really able to work them into the analysis, then we want to have that still in the back of our minds as maybe something that we've missed out in terms of considering that is important. So again, the analysis isn't our only focus. It's just another piece of a puzzle that we're trying to build up a full understanding of the problem. We'll also have to look at the geomorphology. There's a lot of indicators in terms of scarps and tension cracks that open up that give us some clue as to what's causing the overall mechanism. What does everything look like at depth to produce the surface signature that we see? And of course, the hydrogeology is generally very important, as most of the instabilities that we look at are triggered by high pore pressures after a heavy precipitation or snow melt event. So again, with rock slopes specifically, we're generally trying to find these nice big open tension cracks, because this is starting to give us some limits in terms of the area that's unstable. And so we'll be at the top of a steep slope. We'll start mapping these unstable or these open cracks, and then these open cracks basically help us put a limit to our area of investigation, the area that we're analyzing in terms of what looks like it's unstable as opposed to other parts that appear to be stable. We'll add to that then geology and some mapping of structure, joint sets, faults. We represent these usually in a stereo net, where we're trying to put some order to what might be a wide variety of non-persistent discontinuities, maybe of persistences from a half meter to a meter or two. And we try to look for groupings that say that this is a repeating pattern throughout the rock mass, and therefore we can look at the orientation of these structures relative to the slope itself and say how they contribute to the overall destabilization. And we can map springs, areas of discharge to try to gain some understanding of the local or regional hydrogeology that will eventually feed into our models, into our analyses. So essentially we're basically data starved. We're starved for data, and we're trying to find all the pieces of information that we can. So we're trying to map, and we'll walk along the slopes, and we'll map all the visible outcrops. Whenever we have maybe some kind of road cut, or if there's some tunneling activity, some type of exploration at it nearby, we try to get in there to try to get some understanding of how the geology might be different at depth as opposed to on surface. We're basically trying to find and keep our eyes open for anything in the area that might be a source of input and data for us. And we'll do this in some type of organized way. We'll have some type of mapping data sheet that will give us some kind of framework for when we go out, what type of information we're looking for, estimates of the rock mass strength, data details regarding the lithology. There's a number of standardized mapping sheets. This is the one from the International Society of Rock Mechanics, what they recommend. It's published in a new book by Duncan Wiley and Jeff Maw. And again, these are just data sheets that help us to in a very systematic manner, collect all the data that is really relevant towards the unstable situation. So again, rock type description, weathering, information about discontinuities, and an estimate of the rock mass strength. Now, when we talk about things from a very practical level, we don't need to go into a lot of detail. When it comes to rock mass strength, we generally work on some scale, simple scale, and we're talking about the intact rock itself from R0 to R6, so we just have generally 6 grades of rock strength. We can describe these. Maybe we have some laboratory testing so we can give a range of strengths, saying very weak rock, maybe the strength is 1 to 5 megapascal as opposed to strong rock, strength of 50 to 100 megapascals. But again, in the field, you can maybe collect 1 or 2 samples and take it to test, but you're looking at one little sample and saying how does that equate to a large rock slope where you've mapped 20, 30 different outcrops. Is that rock representative? So in general, in the field, you can just take a rock hammer, hit the rock, get some kind of feeling for how sound that rock is, and just make a very general estimate of the strength of the rock. Is it something that you can cut in with a pocket knife, therefore refer to it as weak rock? Is it something that when you hit it with your rock hammer, it makes a ringing noise, so it's a very strong, intact rock? A quartzite, for example, will give a really nice ring when you hit it. And from the intact rock, because this is just part of our assessment, most of our concern is the discontinuities and structures. We'll start going in and we'll start in a very systematic manner mapping the discontinuities and the joints. So we're looking at different characteristics of the joints that contribute to their overall strength. And when we come back and we talk about rock mass strength, we'll talk about this in more detail. But again, we're looking at things that influence the frictional strength along that surface. So its roughness, how open the joint is. Are there any materials, for example clay, that are lowering the frictional strength of that surface? Or maybe if it's calcite from water and precipitation of chemicals, something that's adding a little bit of cohesion and strength to that fracture. And again, the geometry of the joint network, the spacing, how persistent the fractures are, which basically leads into what size blocks you might have and how interconnected the joint system will be. And we'll talk more about this after lunch. And again, just as we have a rock mass mapping sheet, we have joint mapping sheets. And joint mapping is the key tool that we use in a lot of rock slope assessments. We'll go up to a rock outcrop, we'll put a tape measure across the outcrop, and then we'll follow that tape measure in what we call a line survey. We'll talk more about this too because it's, again, one of the key data sets. And we'll just go across that tape measure, and everywhere it crosses a joint, we'll map certain characteristics of that joint. The dip and dip direction, so the orientation of that surface, how persistent it is. Is it persistent on the scale of tens of centimeters, or is it several meters? We'll look at aperture, infilling, and surface roughness, things that are telling us something then about the frictional strength that we're going to estimate later on for our analyses. So these mapping sheets are just a means of telling us, every time we come to a map, to make sure that when we walk away from that outcrop, we have all the information we need to later go back and from the office or from our computer to perform our analyses. Together with the mapping, one of the key tools that we use in a rock slope analysis is some kind of topography information. A lot of it is in the form of topographic maps, but of course with technology now, we're moving more and more towards the use of digital terrain or elevation models. And these are then our easy source of information. The higher the resolution, the better, because again, if we have something that's a 50-meter contour interval or 20-meter contour interval and the slope you're looking at is only 100 meters high, 2 contour lines isn't going to give you a lot of information in terms of maybe some small details in terms of the shape of the slope that might be contributing to its instability. So the more resolution, the better, but with the more resolution, the more the cost. You can fly your own LiDAR, you can fly your own surveys, and construct your own high-resolution maps. And for specific projects, especially those related to a hydroelectric project or a pipeline or something where there's a large, let's say, impact if there is a failure, the money is usually well spent then in terms of getting that high-resolution data set. But maybe in terms of a natural hazard where you're looking within a valley and you don't have the resources or money to pay for high resolution along the entire valley, then just starting with a simple contour map, some information is better than none. And then in the back of your mind, you're always remembering how much confidence you have in the data you're performing your analyses, that you're using to perform your analyses. So with that, photogrammetry is becoming an important source of mapping data. Of course, air photos and satellite imagery. Air photos have always been an important part of the investigation. When we talk about these investigations, we always talk about a desk study. So you start off and you collect known data, you start looking at air photos, you start looking at geological maps before you go into the field, because these help you to start develop an understanding of the problem, so that when you get into the field, you're keeping your eyes open for specific things. One of the new tools that has really been coming on and has a large potential, one of the things that Aldrich and I are working with in Vancouver at the University of British Columbia, is the use of light detection and ranging, basically 3D laser measurement systems, which refer to as LiDAR. One of the problems that we have with rock slope investigations is that the slopes that we're looking at are generally very steep and hazardous, so they're not accessible. So it's easy to say, oh, well, we want to collect as much geological information as possible. But that geology information we're collecting is usually at the toe of the slope, because either the unstable area is inaccessible due to steepness, or it's just dangerous, that you don't want to be there for several hours mapping joints because there's rocks falling all around you. Well, these remote systems now are giving us a means of collecting information where we wouldn't normally be able to collect information before. And they work in terms of being able to produce a very high-resolution point cloud of the surface. So the practical, let's say, limits is that you have to at least be within a kilometer, so from 1,000 meters, within 1,000 meters of this face. And if you can get within 1,000 meters, you can actually get a point cloud of a resolution of 20 millimeters. And if you do that, what you're basically getting out into the computer is a fair representation of that rock slope. And then you can use software that will look at and identify surfaces. So it'll fit this point cloud with a mesh, and then it'll look at neighboring elements and group those that have a similar dip and dip direction. And from that, the output is basically a stereo net. And especially in a mining in situation where we put a lot of money and cost into discontinuity mapping, this is something that to collect this type of data would probably take you a good 6 hours of joint mapping to collect 200 points for a stereo net, whereas the laser scanner can do it within a half hour. Now again, like anything, you don't put all your trust and faith into automatic system. You might want to do some proofing where you pick out key structures that you know the dip and dip direction, or maybe you do a small 1 hour mapping line survey where you have some information where you can look at the stereo net that comes out of the computer and say, yes, that makes sense. I can see these features from the mapping I did, or this direction is equatable to all the planes. Once it starts making sense and you can sort of validate and put some confidence in that, it's then a very important data set. So this is a new emerging technology that has a very high potential when it comes to rock slope analysis. So these investigations are there to try to gain and pick all little pieces of information from wherever possible. So we might have information that comes from archives, old archives of land use, aerial photographs, remote sensing. Basically, these are things that are telling us something about change in land use. And change in land use basically gives us some kind of information or feeling about the age of movement. How long is the slope been moving? How unstable is it? Is that instability increasing, decreasing? Do we see leaning trees, or do we see trees that are straight now, but with the gun barrel or with the bent tree roots? So at one time there was an instability, but things have self-stabilized. So we're trying to gain some information on age of movement. We have information on the geomorphology, so the topography, different field observations of open ground, back scarps, rotated back rotations or forward rotations, tilting of the land. And this gives us information on the type of landslide, what's happening in the subsurface, again, some indication of the degree of activity, the velocity and nature of the movements, and the nature of the rupture surface. Again, because the rupture surface is happening in the subsurface and all our observations are on the surface, we have to try to use those observations in the best way possible to try to gain an understanding of what's happening at depth. Because again, it's easy to show a picture like this and say, oh, well, it's a circular slump. But this is in a 2D section or a 3D depiction on a video screen. When you're actually standing on top of that slope and you're looking at what just looks like a bunch of dirt and rocks, it's harder to get that full appreciation of what's happening in the subsurface. So you have to start learning to read the land and the clues that are being given to you. Maybe in some cases geophysics can come into play. Seismic surveys. There's been a lot of success with using seismic radar. There's a lot of research being done here at the ETH in geophysics looking at radar and the use for rock slides. And this is, again, something that gives you some handle maybe on the depth of instability and maybe some indication of subsurface geology if you're looking at bedded structure environment where you've got bedded geology. And then the geotechnics. Maybe some information from laboratory tests, information from joint mapping, maybe information from boreholes and in-situ measurements. And here we're trying to gain some kind of information or understanding about the rock mass properties, the hydrogeology at depth. We have inclinometers, maybe the location of the rupture surface, or because of the complexity, usually multiple internal shear surfaces, and again, some information on the deep movements and the kinematics. And with all this information, we then feed it into some maybe means of organizing it and giving us some ways to interrogate the data to understand it better. GIS, Geographic Information Systems, have become a very popular tool for doing this, where we can use different maps and layering of maps to try to get some kind of understanding of correlations between different properties and the instability. Again, try to develop a detailed geological cross-section for all rock slope analyses, and in fact, I'd say for all landslide analyses. The geological cross-section is one of the most important things that you'll have, because most of our analyses are limited to 2D, and our 2D analysis is basically copying our geological cross-section, simplifying it a bit, but basically taking a copy of this. And this cross-section basically communicates all our understanding of the depth of the failure plane, the failure mechanism, the materials that are involved, the materials that are involved, especially where shearing is occurring. Most of our information that we get from our geological interpretation to the analyses comes from this cross-section. On top of that, we might do some monitoring. So surface measurements, we might have some geodetic monitoring. And the geodetic monitoring will give us some information again on the nature of the instability. This is an example that I'll use throughout the lectures. This is Campo Valle Maggia from in Ticino. A very large, unstable rock slope that just had been creeping along. And they have a long history of measurements here dating back to 1892, tracking this instability. And from it, we can see information telling us that part of the instability is more unstable than the other half of the instability. And this, again, helps us concentrate our resources in certain areas during the investigation in terms of the areas that are most active, those that are most important. Crack meters, they give us information again on the activity and the outline of the failure. And with a healthy budget, or especially in a mining environment where we have usually a lot of money going into our pit wall geotechnics, we'll have inclinometer measurements to give us some understanding of how that instability develops at depth. Other tools that are coming along now on the monitoring side are along the lines of remote sensing. So global positioning systems, GPS, is becoming an important tool for monitoring instabilities, and so is radar interferometry. So again, there's the question of saying that you're looking at a large valley and you can't just walk up every slope and investigate every slope that's there and to try to find out which ones are unstable and which ones aren't. What we can use, though, is satellite techniques that will look and be able to, through different time periods when they captured the image, look for areas that appear to have moved relative to those that haven't. And I like to think of these as maybe hot spots where maybe something's happening, maybe something isn't, but at least your attention is drawn to it, and now you can go and investigate it, ground-proof it by walking up there, looking for indications of the instability. So it helps you concentrate when you're looking at a large area. It allows you to concentrate your focus on the areas that appear to be moving more significantly than others. Now, if we have this type of information, if we have geodetic information or inclinometer information, we can gain a lot of understanding about kinematics of large rock blocks. So again, this is the Campo Valle Maggia landslide. It's cut by numerous fault zones related to the instability itself. And there are two key blocks that we see here. One that's moving in a translational manner into the valley, down topography, and another block that moves into it. And we can see from the inclinometer data this sort of rotating effect, this sort of smearing of the one block, where we can see that although both blocks make up the landslide, the one block here, the Simamoto block, is only free to move as much as the Campo block allows it. So as the Campo block moves forward, then the Simamoto block moves forward accordingly. So when it comes now to thinking ahead of the game in terms of analyzing the problem and thinking about mitigation, how to stabilize the slope, we already have some understanding that while this is a large volume of rock, 800 million cubic meters, we can't drain all of it or we can't stabilize all of it, but we don't need to. 40% of it is taken up by the Campo block. If we can just stabilize that, then by the kinematics, the Simulmanto block can't go anywhere if the Campo block is stabilized. So by understanding some of that kinematics, we start getting a better understanding of the problem and where to focus our analyses and how to use our analyses to come up with some type of practical solution to a problem or to meet some objective that's given. We've talked a bit about, there's been some mention about trying to predict in time the case history of Kilkenstock where Albin Heim twice predicted failure based on accelerations in displacement monitoring, neither of which came to some type of fruition or came to a catastrophic failure. A lot of our monitoring and a lot of our prediction, or let's say temporal prediction, try to predict when in time a slide is going to fail, comes from monitoring, from displacement monitoring. So we'll monitor displacements with time. We might calculate that as a velocity, so taking our displacements with time, calculating a velocity. There's a technique by Fukuzono looking at inverse velocity, where if we plot the inverse of velocity with time, we can sort of link these points and use that to predict a time of failure. Sometimes it works, sometimes it doesn't. But really, it's at the moment, in terms of, let's say, our state of the art, it's one of the only things that we have to go on. And what I would say is that in some of the cases where it hasn't worked, it's because there hadn't been enough focus or understanding or focus or attention placed on trying to understand the underlying mechanism. They've just tried to blindly make a prediction based on surface movements without really understanding maybe the nature of the failure. And there's been a lot of work done on these. The use of this, if you go into the literature, there's one, maybe two successful cases of forward prediction. What we're actually really good at is predicting something that's already happened. So our back analyses. We're very good at going back, finding a failure that occurred, doing all this sophisticated analysis and saying, look, our analyses say that it should have failed. It should have failed at the time that it actually failed. But saying that in hindsight is different than actually doing it in forward prediction. And again, very few cases. Chuquicamata, which is a mining failure, is a pseudo forward prediction of using these type of techniques. It's one of the few that are out there. But where this technique has really gone is not thinking about an outright prediction, but thinking about it in terms of risk and the type of warning that should be issued. So a lot of work is being done in Italy by Giovanni Crosta and others in terms of looking at different thresholds of how alert you have to be based on certain accelerations in these displacement time graphs. Other tools that we can use in terms of getting some feeling for the zone that might be endangered. Aldrich has done a lot of work looking at what's referred to as a rockfall shadow angle. So looking at, again, reading the geomorphology, reading the ground, looking at where talus and where rockfalls have in the past fallen, and using that as an indicator along a valley system as towards to where there might be instability. So a measurement maybe between the apex of the top of the talus slope and where the farthest outlying block is. And so using this as to make an initial assessment, your first assessment of risk to developments near a steep slope. Similarly, Aldrich has mentioned the Fabrishung angle and basically the travel angle run out. This has also been used where they've plotted major rock slides that have occurred in terms of their volume and how far they've traveled. So trying to make some correlation between rock slide volume and the area that might be then endangered by these by a mobile rock avalanche.